Today we want to start a new chapter called linear programming, and we want to learn about simplex method. This is a third method for solving mathematical models or linear programming models. As may you remember, graphical methods was the first method, corner point was the second one. Today we want to start the third method, which is called simplex method for solving linear programming models. So for today, we want to learn the following items. After completing this module, you will learn about how to convert linear programming constraints to equalities with slack, surplus, and artificial variables. Also, you will learn how to set and solve linear programming maximization problems with simple established and objective function. Um, there used uh, uh, as you can see, I have removed these items from your textbook, and if you have a question from them, you are more than welcome to ask me later, but they will not be in your final exam. And okay, so we are going to cover items up to this module 4. Let me take pen. This module. And subsections of 1 to 4 will be in your course, and the rest of it is not in your course. However, you are more than welcome to review them, and if you found any problems, you can ask me later, okay? So, for today, we want to start with simplex method and other things. What is the difference between simplex method compared to previous two methods, which are graphical method and corner point? So most of the real life problems have more than two variables. So when you have more than two variables, you cannot use graphical method. And for example, if you have x1 to x100, so you can imagine that how many corner points you may have. So it is difficult to find which one is the optimal solution. So when you have more than two decision variables, using simplex method looks much more efficient. So two variables was the characteristics of graphical method. So in graphical method, we were just solving problems with two variables, but in real world, so we are making decision with more than two variables. Okay, in this case, we need to another method. This method is called simplex method, and simplex method examines the corner points in a systematic fashion. A simplex method use a corner point method, but in a systematic fashion. So, um, uh, um, um, so do you remember in the second method that we learned it was moving from one corner point to other corner point, and the method evaluates all possible corner points and finally finds that which one is the optimal. Okay, so that's the way that it works. However, when the problem size gets very large, this doesn't look a good way to evaluate individual corner points. So instead of evaluating individual points, you will just select the most appropriate points in simplex method. The points that um, add the value to objective function more than other corner points. You don't need to evaluate all the possible corner points. Only points that add value to objective function will be reviewed. Okay. And let me draw it a graph here. For example, we have a variable x here and a decision variable y here. And these are for a constraint. And here we have visibility area or region. So we are located here, corner point 1, corner point 2, corner point 3, and corner point 4. So in corner point methods, you need to evaluate all of these points in objective function and find which one maximize your profit or minimize your cost. But in Simplex method, we always start from this corner point 1, and we evaluate these two neighborhoods, corner point 2 or corner point 4, and evaluate which one add to your objective function. If corner point adds to objective function more, we move from corner point 1 to corner point 2. If corner point 4 adds more than corner point 2, we move from corner point 1 to corner point 4. We'll reach to these later. Don't worry about it. I just explain it briefly to understand what is difference between corner point method and Simplex method. So in Simplex method, we are evaluate points, and we don't need to evaluate all the points we have. So let's review some specification of Simplex method. We are going to repeat it several times. First of all, it is an iterative process. So what does it mean? It means that there are a set of steps that they should be repeated several times up to reaching a condition that we have reached to optimum solution. Then you will stop. Okay, so before reaching optimum solution, you need to repeat them several steps, and that's meaning of iterative process. Several steps should be repeated several times. Each iteration improves the value of objective function, and in each iteration, the value of objective function will be improved. And that's our goal. We want in each iteration, we get some improvement in the objective function. So if we notice that in an iteration, our objective function is not improving, you will stop. Okay, so that's another condition. We will stop if you don't get any improvement in the objective function in each iteration. So this method, which is Simplex method, yields optimum solution and other valuable economic information. Okay, so we mostly focus on optimal solution. This method is going to bring us that value, optimal solution, but you can find many economical information about extract many economical information from Simplex method, but we don't focus on them. They are the benefit of using Simplex method. Here we are just looking for optimal solution from Simplex method. This is the problem that we used in previous chapter, which was a graphical method and corner points. We are going to use same problem. So as you remember, it was a furniture company. They were trying to find the solution for number of chairs and number of tables. These two are all decision variables, the number of tables and the number of chairs. As we had an objective function, the goal was to maximize our profit. We normally write it in this way: maximize of z is equal to, this is the objective function, is equal to the rest of it. So $70 per table and $50 per chair. We had some constraint. We write constraint after subject to. Always write them the constraint after subject to. And we are, here we have two hours of painting for table, and 1 hour of painting for chairs. That must be less than the maximum hours of painting available, as same for carpentry. At the end of this model, we have non-negativity constraint, which means that the number of table and chairs cannot be a negative number. It can be zero, but it can never be a negative number. So let's start with simplex method. Before we get started officially, we need to learn how to convert there are several steps to using simplex method. First of all, you need to convert all constraints to equation. What that means? When you have inequality, for example, as you can see here, this is inequality. When you have greater than or equal to sign, or less than or equal to, we need to convert them to equations that you use equal sign. Okay, so this is the first step, that we need to convert inequalities in constraint. You can see them here to equality. How we can do that? So we are using some decision variables. For example, when we have less than or equal to, we use a decision variable. We call it a slack variable. So when we have a less than or equal to, we use a slack variable. So what can we do? How we can convert inequality to equations equal with equal sign? Here we are going to use two different concepts. One of them is the slack variable. Okay, a slack variable. By adding a slack variable to less than or equal to constraints, we are able to make inequalities into equations. Okay, this figure could help you in order to understand the concept of, a slack variable. So for the first constraint, for example, this constraint, first constraint, so you can see 2t plus 1 multiplied c is less than or equal to 100, this constraint. So if we add a slack variable to the left-hand side, we don't know about it. We can reach 100. So for the first constant, let's imagine that this bar here is 100 for, and this guy is trying to reach it that is equal to 100. Okay, 100 units of painting. So right now the head of this guy, if this guy is below this bar, okay, so this person should push the bar, okay, and move himself up to this bar, okay. So his head should pass it, okay, pass this bar. So in this case, we need to an extra push, which I call it plus S. I call this gap plus S. That is a slack variable S1. Let's look that this guy who is reaches um, uh, uh, equalities. So right now, this guy is less than 100, but if I add a parameter or a decision variable is, so I move the heads from here to this spot. And then this person will be able to reach 100. So we have another concept. So both of constraint, the first constraint and second constraint, have a less than or equal sign. So for both of them, we just need to add a slack variable. You can see for the second constraint, we are using a slack variable as well. We call it S2, two decision variable. Both of them are a slack variable. But sometimes we have a greater than or equal to constraint. In this type of constraint, we are using a decision variable. We call it surplus. Okay, you can see here. Oh, there is not. So we call it a surplus. You can we have this is another concept. So it's in surplus what we have in totally opposite. So if I consider bar here in the right hand side picture as 100, for example, imagine that we have another constant that is greater than or equal to 100. We have a constraint that must be greater than or equal to 100. And in this case, this guy has put his head a little bit above this bar. So you can see that the head of these guys is above this bar. So if I consider bar exactly the same as 100, okay, and in this case, this guy has uh, is above this guy, this bar. How much? Let's say this is the maximum. So and this amount or extra amount, we call it surplus variable. So I have to deduct the value of SU that is called surplus because it is an extra. And so if I deduct, if you don't talk, please make sure that you are muted. Okay, thank you. So for greater than or equal to constraint, we need to deduct surplus from left-hand side. If you deduct it, you can reach an equality or equation. Okay. This is totally opposite of a slack variable. In when we have a less than or equal to a constraint, we added a slack variable, but in greater than or equal to constraint, we deducted a surplus variable. Okay, so this is the first thing that this is the first step for using simplex method. We need to convert all constraints to equations with equal sign. If we have a less than or equal to constraint, we need to add a slack variable. If we have a greater than or equal to constraints, we need to deduct some surplus variable from the left-hand side to reach equations. Okay, so you can see, for example, in an optimal solution, we should produce 40 table and 10 chairs. For example, after solving the problem, you reach this number. If you put them in, for example, the first constraint, this is the first constraint. So if you put them, and you can see that the value of S1 or the first slack variable is 10. What that means? This is the max, this is the it is So it means that we still had 10 more hours in the painting, but we didn't use it. Okay, that's the mean of not using resources appropriately. So it is still we could use 10 more hours, but we decided not to use it. So you can do the same analysis for the second constraint. For example, if you put the value of T and C in the second constraint and find the value of S2, you can say that how much of your resources has not been used. Okay, so there is another, there is a second step to using simplex method. This is the second steps. The first step was in converting all constraints to equations. And the second step is adding all variables into all equations, including objective functions. As you can see, for both of constraint here, we add the both decision variable. So in the first constraint, as you can see here, let me erase some data. So in this constraint, we have not uh, uh, this variable S2. How we can add this one to the first constraint? We can add it with a coefficient of 0. If I add this one to the first constraint with a coefficient of 0, 0 multiply S2, it doesn't matter. Everything is same as before. So it doesn't change anything. Okay. Also, we can add S1 to the second constraint. As you can see, we have not any S1 here. We can add S1 with a coefficient of 0 here. S1 plus. So in this way, as you can see here, we include all decision variables in to all equations, including both constraint as well as the objective function. As you can see, for objective function, we also add both decision variable with a coefficient of 0. Okay. So in this way, all decision variable included in all equations, objective function and constraint. This is the second steps for starting of using Simplex method. Is it clear for everyone? If you have any question, don't hesitate to ask.
It's clear, thank you.
Oh, great. You're welcome. Okay. Let's move to next concept, iterative nature of Simplex method. The Simplex method visits each corner point to improve the value of the objective function. So do you remember in graphical solution method, we had some corner points. So corner points, um, uh, let me draw it here. Corner points, and this is t, for example, decision variable t, and this is decision variable c. And we had two constraints, corner points of 1, corner points 2, point 3, and corner point 4. So this is the feasible area, and this is a maximization problem. Okay, for this feasible region, we need to move from point number 1 to point number 2, 3, and points number 4. So using corner points, it really doesn't matter which points you start. So it really doesn't matter because you need to evaluate all of these 4 points. But in Simplex method, it's very important that we start from this point 0. We always, in Simplex method, we start from corner point 1, when both of decision variable are equal to 0. T is equal to 0, and C is equal to 0 in these points. We always start from this point in Simplex method. So it means that all your calculation, all your evaluation start from this point. And I will show you in next slide how to do that. Okay. Why? Because it is like so if you put 0 instead of t and c, you can reach the value of objective function as 0. So this is objective function, and z is equal to 0 in this point. So our profit will be 0. But we are not happy with this profit. We need to move to next corner, either corner point 2, this corner points, or a corner point 4. Which one that gives us the best results? Okay, the point related to Simplex method is that you don't go randomly. For example, you don't go from a corner point 1 to corner point 3. You cannot go randomly. We evaluate neighborhoods, corner point 2 or 4, and based on which one gives us more profit or maximize our profit more, we decide to move this side or this side. Okay. This is another concept you need to learn, that we always we start in Simplex method from this point. So when both of decision variable are equal to 0. So now we have some a temporary concept here that is a basic variable and non-basic variable. So this is a temporary name for variables that is not something in nature of variables. These are temporary properties. These are not the property forever. Okay, so this something that can change over time. Some variable can be basic variable in one iteration and can be non-basic variable in another iteration. So this is not a property forever. At a particular time or at each corner point, we have some variable, consider some variable as non-basic and consider some of them basic variable. So what is the difference between them? All variables that are equal to zero, we consider them as non-basic, and all variables that have a value more than zero, we consider them as basic variable. For example, in corner points 1, the value of t and c are equal to 0. So when variable are equal to 0, we call them non-basic. So the value of t and c in the corner points 1 are equal to 0. So which decision variable is is basic variable in the first corner point? So in this corner point, the value of S1 S-like variable, the first S-like variable and second S-like variable or basic variables, as you can see here, the first corner point here in this point. So now we are ready to start with Simplex Tableau. But before we start, we need to convert um, we so let me review the steps again. First, we convert all constraints to equations. So we have equal sign in both constraints. After that, second step, we add all decision variables to all equations. You can see S1 and S2 here, and add S2 with the coefficient of 0 here, and S1 with the coefficient of 0 here to the second constraint. So before we start Simplex method, we need to convert objective function in a way that all numbers be be placed in right hand side of equation, and all decision variable be placed in the left hand side. As you can see, the object function is z. Maximum of z is equal to 70 multiplied t plus 50 multiplied c plus blah, blah, blah. We can convert this one, and we can write z here and move all of decision variable in this side to the left hand side and change the sign behind that. Okay, so z minus, if I move 70 multiply t, the sign of it can change to negative, and can write it here 70 t minus. Now I move 50 and multiply c to left hand side of this equation, 50 multiply c minus 0 S1 and minus 0 S2. that is equal to, there is any number left here? No. So we just place all numbers in the right hand side. As you can see, for constraint, we have all numbers in the right hand side and all decision variable in the left hand side of the constraint of these equations. As well for objective function, we moved all decision variable to the left hand side and all the numbers to right hand side, and there is not any number here. We just write 0. So this is objective function. Now we want to learn another interesting concept, which is simplex tableau. Okay, these are like a table that we are trying to work on it. This is like a cooking table uh, that you are preparing something on that. Uh, so it's called a Tableau. Okay, Tableau are very interesting tools that help us in order to find the optimum solution. What do we see in simplest Tableau? We see the basic variable here. The first row, we can see basic variable, and all of decision variable have been wrote between here. We have all decision variable, including objective function. The value of objective function, you don't need actually this one. Okay, you don't need to write objective function here. Z. We have all decision variable, including T, C, S1, and S2. After that, this is right hand side. All values in the right hand side. So the first row show us the objective function equation. This objective function here, you can this one equation, and this one is the first constraint, and this one is second constraint. So you need to write objective function, and same as the number of constraints, you need to add rows below the objective function row. Okay, so we have two constraints, so we need to add two rows here. So the right hand side of objective function is 0. So we just put it here. And the right hand side of the first constraint is 100. We write it here. And the value of right hand side of the second constraint is 240. Okay, so uh, um, so we need to choose for object function. So we just need to write z here. It is same in all iteration. It doesn't change. So, but for second, the first and second constraint, so which variable is a basic variable? We need to select. So how we can choose which one of these variables can be basic? Let me add some data here. We always choose the variables with a coefficient of 1. Okay, we choose variables with coefficient. In the first constraint, which variable has a coefficient of 1 in the first constraint? So S1 and C has a coefficient of 1. C and S1. In the second constraint, So which variable has a coefficient of 1 is 2. So for first row, we can choose S3 or S1, but we prefer to choose always slack variables. They are more preferred than the main variable, decision variable. Okay, we just write S1, and for the second constraint, we have just one option, and we just write S2 as basic variable. So do you remember the meaning of basic variable? The basic variable, the value of them are greater than 0. These are basic variable, and non-basic variable are equal to 0. So as you can see here, the value of S1 is equal to 100, and the value of S2 is 240. And what is the value of T and C in the first iteration? In the first iteration, the value of T and C is equal to 0. These two are or a non-basic variable in the first simplex tableau. This is the first simplex tableau. Let me move on. So how this is the first simplex tableau, and we know that this is a maximization problem. So here, this is a maximization problem. In maximization problem, how so this table, this simplex tableau, is related to corner points 1. If you remember, in corner point 1, the value of T and C are equal to 0. In this point, the value of T and C are equal to 0, and the value of S1 and S2 are equal to 100 and 240. Okay, the first simplex tableau related to first corner point. Each simplex tableau related to one corner point. So the first simplex tableau that is related to corner point 1. So we need to check that this is optimal solution or not. In max to check that, we just need to see this row, the objective function row. Okay, in this row, in maximization problem, we just need to check that there is any negative number in the objective function, and in minimization problem, we just need to check that there is any positive number in objective function row. So we just check this row. Let me use highlighter in this row. Okay. So there is any negative number here? Yes, there is two negative number, this one and this one. So that means that this is not optimal solution. We can improve objective function. Okay, so we need to in each so we have two negative number. That means this table is not this table it doesn't show us the optimal solution, and this is not the optimal solution, the value of z, and we can improve it. So what we can do to improve it. So we just need to enter one of these non-basic variable, T or C, with negative number into basic variable, and leave one of these two basic variable, S1 and S2, from basic variable to non-basic. So we should select one of P or C to be entered to some basic variable. Which one we should select? The decision variable with the most negative number. Which one is biggest negative number? Minus 70 or minus 50? Minus 70. So I just decide to enter this decision variable to basic variable. I just selected the decision variable with biggest negative number to be entered here. I just decide to move it to basic variable and extract one of these to basic variable S1 or S2. So as you can see, we choose the most negative coefficient, that is minus 70, um, uh, to be entered to basic variable. So how we can choose which one of this one, S2 or S1 or S2, must be go out from basic variable. We should get rid of one of these the decision these two basic variable to be non-basic in next simplest tableau. How we can check this? So there is a simple approach. So you just need to watch this column. So we just need to divide this number by this number. Okay, we divide this 100 divided by 2 and 240 divided by 4. And find out which one gives me the lowest minimum ratio. 100 divided by 2 is equal to 50, and 240 divided by 4 is equal to 60. Okay, and choose which one gives me the minimum ratio. As you can see, 50 is minimum, is less than 60. So I just selected that S1 must be left this table, basic variables. Okay, so as you can see, there's a simple method that you can use to choose which one of these two basic variable kick off from simplest tableau. Okay, so I just choose the decision variable with the most negative number to be entered to table as the variable that has minimum ratio by dividing right hand side to this number in this column um, to be left this table. So, but there is an important note here. So we can, if you have in this column, the column related to variable, you need to enter to simple example. If you have when you have a parent 0 or a negative number, you don't need to divide the right hand side to them. If you have a 0 or negative number in this column, so you don't need to divide this by the number. You just ignore it, as you can see here. When we have a negative, we cannot, you just need to ignore a negative ratio, or when we have a 0 in this column. So for example, instead of, or is some, for example, instead of 2, I have just 0 here. Okay, so I just ignore it, and I have only one option, S2. So I just decide to uh, extract or move out S2 from basic variable. If instead of 2, um, I have a 0 in this column. So This is a very important note. Please remember that. So we have some concept here. Um, let me. So this column that we decide to enter this decision variable called pivot column. We call this column related to parameter that wants to be entered is called pivot column. And the row related to it, S1, that we are going to set it out of basic is called a pivot row. And the intersection of these two column and row is called pivot element, as you can see here. So this decision variable that wants to enter is called pivot column. This row related to a variable that is going to set it out of basic is called pivot row. And intersection of this column and this pivot row is called pivot element. Okay, so uh, uh, so we decide to enter t as basic variable and kicked off from S1. So we need to update all numbers in this table after replacing t and S1. So here we just replaced t with S1, and now we need to update all numbers in this table. So you don't need to write this column. We don't need it. How we can update number? We have two formulation here that help us to update all numbers in Simplex Tableau. For new pivot row, for this row, we can use this formulation: current pivot row divided by pivot element. So in this row, we just need to divide all numbers in this row, in this row, by this number, pivot element 2. 0 divided by 2, 2 divided by 2, 1 divided by 2, and 1 divided by 2, and 100 divided by 2. So in this way, you can update all numbers in pivot row. For other rows, including Z, this one and this one, for other rows, you can use this formulation: current row minus pivot column coefficient multiply new pivot row. Let me show you here. So for pivots row, for this one, I just use the first formulation, this one. How we can do that? I just need to divide all of them by 2. If divide all of them by pivot element, which is 2, I can update all numbers here as here. 0 divided by 2 is equal to 0. 2 divided by 2 is equal to 1. 1 divided by 2 is equal to half. 100 divided by 2 is equal to 50. For other columns, other rows, as you can see, how we can update all numbers here. There's a simple formulation here. We can use occurrence. For example, for this cell, I use this formulation, current row. What is the value in current row? 1 minus pivot column coefficient. Pivot column, this is pivot column. Here, this is pivot column. Coefficient minus 70. Multiply new pivot row. New pivot row, and this is 0. That is equal to 1. So I just write it 1 here. What about, for example, for this one? Let me update this cell. So current row. What is current row? 240. 240 minus pivot column coefficient. Pivot column, this is pivot column coefficient is 4. Multiply 4. Multiply 4 multiples. New pivot row. What is new pivot row? 50. That is equal to 40. Okay, so you can see all equations for all of these cells here. In this way, you can update all numbers in this table. Okay, all other rows. So in this table, as you can see, we have t here as a basic variable and s2. We replaced t with s1, and this is the second simplest tableau. This is the second simplest tableau. Now we need to check that this is optimal. This simplest tableau, the second simplest tableau, is optimal or not. We need to check optimality or optimal condition. How we can check it? Do you remember? Do you have any idea how we can check that this is optimal solution or not? We need to check this one. This is help. Do you have any idea?
If anyone has negative to it, it will not be optimal one.
Okay, thank you so much. That was great. Yes, in the objective function, in this row, the first row, we just need to check that there is any negative number. Yes, there is one negative number. So this is not optimal. As there is a negative number, we can improve the objective function. Now the objective function is equal to 3,500, but we can improve it. The value of t is 50 and the value of s2 is equal to 40. But we can move to another simplest tableau and we can improve the objective function. The objective function, do you remember that it was maximization? We can increase the value of objective function in the next simplest tableau. How we can understand that? With finding a negative number in the first row. So we should enter this, we have just only one negative number. So we just decide to enter c as a basic variable. Here, we have only one option. This is the new pivot row, pivot column. So this is pivot column, new pivot column. Okay. So now we should, after that, we decide that to enter one decision variable with negative number to basic variable, we should decide which of these two t or s2 must leave the simplest tableau. How we can decide about it? So it's easy. We just need to divide the right-hand side by this number, 15 divided 50 divided by a half, that is equal to 100, and 40 divided by 1, that is equal to 40. Which one is gives me the minimum ratio? This one gives me the minimum ratio. So I decide to uh, 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 extract or leave S2 from Simplex Tableau and replace it with C. So after that, we need to, so this is pivot column, pivots, new pivots row, and this is the minimum ratio S2. So we need to use Guess Jordan computation formula techniques to update all numbers in table. If you remember, we need to one formulation for pivots row, this one, and another formulation for these two rows to update all numbers. So you know the techniques. After updating all numbers, you can see we have the C here, and we replaced S2 with C. So we need to update all numbers here. This is the new table. We updated all numbers in this table. So in this table, as you can see, and this is the third Simplex tableau. As you can see, we have not any negative number in this objective function. So this is optimal solution. In optimal solution, the value of t is equal to 4,100. The value of c is 40, and the value of t is equal to 30. So you need to produce 30 tables and 40 chairs to maximize your profit. That would be equal to 4,100. This is optimal solution, as you can see. And this is the last Simplex tableau. There is any question? If you have any concern, please let me know.
No, it's all clear. Thank you.
You're welcome, Gate. So let's me move on. This is a review of what we did here. So, this is another example of maximization problem. We can review it again. The first step is converting all inequalities to equations. How we can do that? We just need to add a slack variable to left-hand side for first constraint, and add another slack variable to the second constraint. We call it S2. So this is the first step. The second step is writing all decision variables in all equations, including objective functions. So I can add S1 and S2 to objective function with a coefficient of 0, S1 and S2. So I will add S2 to the first constant with a coefficient of 0, and S1 to the second constraint with coefficient of 0 as well. So in this way, I convert all constraints to equations, and all of them included all decision variables. So I'm after moving all decision variables to left-hand side of this objective function. In this way, I'm ready to write simplex tableau. The first simplex tableau, 9x1 and minus 7x2 minus 0 s1 and blah, blah, blah. So in this way, we can use simplex tableau. You just need to put all numbers here in the simplex tableau. So what about the minimization problem? We have some differences between maximization and minimization in using simplex method. So what is the difference? Generally, we are having greater than or equal constraint in minimization problem. So as you remember, when we have greater than or equal to, we have to deduct a surplus variable from left-hand side. So we need to deduct a surplus variable from left-hand side, as you can see here, and convert this constraint to equations with equal sign. So, but if you remember, we always start from the corner points 1, that the value of the main decision variable x1 and x2 are equal to 0 in these corner points, in this point. If we imagine that the value of x1 and x2 in the corner point 1 is 0, what is the value of s1 in this corner point? Here, in this corner point, how much is the value of s1? So s1 cannot be a negative number. S1 is always positive, as same as s-like variables. So how we can solve these issues? So we can add another decision variable to these kinds of problem, these kinds of constraint with greater than or equal to with using an artificial variable. So when we have a let me erase some line here. So when we have some greater than or equal to or equal constraint, we are using artificial variable. So in this type of, so when we have a greater than or equal to or equal constraints, we always add artificial variable. So let me show you in one example how we can use it. We call this a method. Why? I will explain it next slide. So this is an example. I will come back again and I will explain in methods. So as you can see, we have three, this example is a minimization problem. We are trying to find the minimum cost. So we have three constraints here. X1 plus X2 is equal to 1000. X1 is less than 200 and X2 is greater than. So how we can convert it to an equation? X1 can be easily converted to equation with adding a slack variable to the left-hand side. And we know that for greater than or equal to a constraint, we need to select a surplus variable and artificial variable, as well as for equations. So you can see here, there's, how I can do that? Let me write it here. This is the first constraint, x1 plus x2 plus, I need to add an artificial variable to the first constraint, a1. I will call it a1, artificial variable. That is equal to 1000. For second constraint, x1, I just need to add a slack variable. So I just add the first slack variable that is equal to 200. Why? Because it is less than or equal to constraint. And for greater than or equal to a sign, I just need and a surplus variable and also an artificial variable as well. I just deduct a surplus variable. I will call it S2. This is a surplus variable plus the second artificial variable. In this way, I converted all constraints to equations. So if I add an artificial variable to left-hand side of this um, um, constraint, as you can see here, in the first corner point, when the value of x1 and x2 are equal to 0, so S1 cannot be a negative number. But if you put the value of A as 800, so you can consider the value of S1 as 0. So S1 cannot be a negative number, as you can see here. All slack, surplus, and artificial variables are always a positive number or equal to 0, but cannot be a negative number. So this is the way that we are using artificial variable. We are using them in equal or greater than constraint. We are using surplus variable in greater than or equal to constraint. And when we have just less than or equal to constraint, we are using a slack variable. Okay, so for this type of constraint, we are using surplus artificial variables or slack variables. So why we call it a method? So if you remember in the when we are using a slack variable, we added this type of variables to objective function with a coefficient of 0. We added them with a coefficient of 0. But here, when we have using an artificial variables, we are just using a big number as a coefficient, not 0. So how we can determine the big number? That can be any number. You can imagine that 1,000, 1,000,000, any number, any big number. But in maximization problem, we just need to add a negative big number. But in minimization problem, we are just add a positive big number. As you can see in this example, that is minimization, we need to add artificial variable to objective function in minimization problem with positive big number. So I just add the first artificial variable with a big positive big number to objective function. and second artificial variable n a2. I also need to add all slack and surplus variable as well. So with a coefficient of 0, I just add S1 with the coefficient of 0 and add surplus variable with the coefficient of 0 as well. The objective function. In this way, I can update objective function equation that includes all decision variable, including a slack variable, surplus variable, and artificial variables. But here we have a different coefficient for artificial variables with a big number. So here yeah, if we use, as you can see, we have just two decision variable. We always can use, when we have two decision variables, we can use graphical method, but the simplex method that is more efficient when you have more than two decision variable. So here, this is the graphical method. You can find where is the feasible region, and just check corner points and find which one of these corner points is the optimal solution. We just putting the value of them in objective function equation and find that which one gives you the minimum value. Why? Because this is a minimization problem. However, we are trying to learn how we can use simplex method. If you just convert all constraints to equations and adding all decision variables to all equations, you can reach this model. You can see in the objective function, we have S1, S2, and artificial variable, and also add all decision variables to all constraints. Here we have a slack variable and surplus variable with a coefficient of 0, and second artificial variables with a coefficient of 0. This is exactly the same as this model, but here I just added all decision variables to all equations with a coefficient of 0. So here, for example, I have just one slack variable. I added other variables with a coefficient of 0 to this constraint, and consider equal sign for all of them. After that, I just need to move this side of objective function to this side and consider z minus the rest of it equal to 0, because there is not any number in objective function, and put all of them in this example, we imagine that the value of n is equal to 100. Okay. After that, we just need to put all numbers in here. So you can find the value of, after you moving the value of the x1 to this side, the coefficient of 5 can change to minus 5. And you just need to input all of this data in the table. So for example, the value, the coefficient of x1 in the first constraint is 1. So the coefficient of x2 in the first constraint is 1, and coefficient of, for example, a1 in the third constraint is 0. You just need to input all of these coefficients into this simplex tableau. This is the first simplex tableau. So here, I just imagine that the value of n is equal to 100, a big number. But this is a minimization, and I just consider a positive big number. So it is very important to remember that. So here, we have first simplex tableau, but if you put the value of in this table, x1, x2, and s2 are So we just need to choose which one of these decision variables be our basic variable. So I just choose when we have artificial variables, we always selected them first. So in the first objective one, in the first constraint, I have an artificial variable. I just consider it as a basic variable. For the third constraint, I have another artificial variable. I just consider it as a decision, as a basic variable. Why? Because I'm trying to get rid of them. So I will just put them as a basic variable always into Simplex Tableau, the first Simplex Tableau. For the second constraint, I'm looking for a variable with a coefficient of 1. So I have x1, I have s1 with a coefficient of 1. So I prefer to select s-lag variables or surplus variables. So I just put s1 as a basic variable. So other variables, including x2, s2, are non-basic, and the value of them are equal to 0. So the value of x1, x2, and s2 are equal to 0. So a1, the value of a1 is equal to 1000, and the value of a2 is 150. So and the value of s1 is 200. So if you put them in the objective function equation, you can find that the value of objective function is 115,000. So the first thing that when we have artificial variable, the first thing that we should do is getting rid of them. How we can do that? So we can use this formulation here to get rid of them. How we can use them? For this row that shows the objective function row, we can use its old z row. So plus 100 a1 the first artificial row plus 100 multiply the second artificial row. If you have three artificial row, so you just need to multiply the value of m to that row. Okay, this is the value of 100. So you can see that. For example, this number, the other rows stay same. But we just update the objective function row, as you can see. For example, this cell can be updated in this way. The O's row, Z row. What is O's row -5? Let me write it here. Plus the m value. What is the m value? 100 multiply a1 row. What is a1 row? This is the plus the m value that is equal to 100 multiply the second artificial row. This is the second artificial row. So, -5 plus m that is equal to 100 that is equal to 95. So this cell is 95. and you can update it this one as well. How we can do that? You can use this formulation. O's row, that is 0 plus 100 multiply A1 row, this one, plus 100 multiply this one. So in this way, I can update it objective function row. So after updating the objective function row, you can reach this one, this table. So first of all, I just check. So in from this simplest tableau to end, we don't need to consider these two column artificial variables. Okay, so this table is optimal or not. This is a minimization problem. So we should check that there is any positive number in the objective function row or not. In this objective function row, there is two positive number, this one and this one. We should select the one that with biggest numbers. Okay, I just select x2 to be entered to Simplex tableau. And which one should be go out of this table? So I have a 0 here. I don't need to find any ratio for that. So I can use this formulation. I just divide the right-hand side by this number 1 and compare it with a deviation of 150 by this number, as you can see. So I just find that which one is minimum, gives me the minimum ratio, 150. Okay, so I just decide to enter x2 and set a2 out of basic variable. So this is pivot column and this is pivot row. And this is pivot element 1. So I can easily update it. As you can see, I just replaced x2 here. And this is the second Simplex tableau, third one, and last one. Uh, So after that, you find that there is any positive number here. Yes, there is two positive number. I just select this one to be enter because this is a biggest number. 95 is more than 94. So which one should be left from this basic variable? So this is a 0. I don't need to consider it. And then you just need to divide 850 by 1 and 200 by 1. So you can reach these numbers, this minimum ratio. So which one is minimum? This one. So I just decide to kick off from S1. So after that, after updating all numbers here, you reach to this Simplex tableau. And in this table, there is another positive number. So I just decide to enter S2 as basic variable. And this is a 0, and this is a negative number. If you remember, we don't need to consider them when we have a 0 or negative number. So I just one option. So I just leave A1, leave A1 leaves the table, and S2 can be entered to Simplex tableau, the next Simplex tableau. You can see there is not any positive number in this row. So this table, the last one is optimal tableau, and the value of Z is equal to 5,700, and the value of X1 and X2 is 200 and 700. So this is optimal value. Is there any question? This is the last thing we need to learn about simplest tableau. I know that it looks a little bit complex. You need practice to get up all uh, techniques we learned together. Okay, watch this file as many times as you can. This is the correct for all of them from this uh, chapter to the end. And not only watching, I'm repeating it. You know, many times you should do practice for this course. Without practice, you will fail. Okay, that's really easy. I will upload some practices on Moodle this afternoon, and you can see that and practice more. Okay, do you have any question?
No, professor.
No,
Great,
professor.
thank you so much, Garrett. Have a great weekend. Uh, and thank you so much for attending to the class. Let me stop recording.